And our next presenter is Biliskov, who is CEO of CodeEasy, and he will instruct us in seeing through the lens of transformers, a new era in computer vision. The presentation will explore core components of transformers, the nuances of self-attention, and the factors contributing to their remarkable success in vision tasks. Igor, please welcome, and I'll make you up this time with a coffee break that will be shorter.
Hello, greetings everybody. Good morning. So let me just try to, okay. First off, I think Igor made a great point and had a great presentation about using, like, high-level image recognition. So my presentation will be something of, let's go to the deeper levels and try to find out how this actually works and how the computer actually sees and tries to get some meaningful information. Sorry for my voice, I just woke up sick this morning. So, okay, so how many of you are using computer vision in your day-to-day operations? 1, 2, 3 hands. Okay, have you used vision transformers yet? Okay, nice, nice. Okay, so the idea is that vision transformers started to gain traction for maybe a year or two now, and we've seen more and more companies starting using them because they have some nice properties. We're going to explore those properties, and we will try to see how we can actually use them in our own projects. What do we gain, what do we lose, and where the future is getting. Okay, so my name is Biliskov. I'm from Split, Croatia. CEO of company CodeEasy. We do AI implementations for clients, we do computer vision, and we do custom application development. Basically, what we saw is that more and more clients want us to do different integrations, connecting to different services, and they want fast prototype. So I will try to explain how can we use these new technologies to actually build that and try to incorporate in your workflow. I'm also doing my PhD thesis in the field of artificial intelligence, computer vision. So there I'm solving a problem of how can we see objects that are underwater. Basically, if you do detection for something that's underwater, imagine you're taking a picture of something that's underwater with a drone. You have like physical, biological, and chemical properties of a water which distort the image, and you cannot do proper image classification or object detection. So we're trying to create an algorithm that will make some better object detection on those images and try to predict those properties and remove them from image, and then try to do object detection on those. So that's the brief intro. Okay, so let's just do quick reminder on classical convolutional neural networks. So basically this is, just let me, okay. So this is like a normal image, and what you have usually is that you have a convolutional layer, pooling layer, and then you stack more and more convolutional layers until you get the, so you stack more and more convolutional layers until you get to some depth where you have extracted features that you need. So how convolutional neural networks started, because before we had handcrafted kernel features, right? And then now we have convolutional layers that try to guess and try to learn what the best kernels would be to apply to image to extract the features that we want. I'm here talking specifically about image classification problem. So we stack and stack and stack more and more convolutional layers until we connect one fully connected layer at the end, which is of course trainable, and then we can extract, we do softmax, and we now have the class of our element, and that's fine. Usually what we learn through the years is that if you go too deep with the convolutional layers, you lose some stability and you get strange results, basically, which was solved by using residual connections and skip connections and stuff like that, which allows us to propagate some of the stuff to the lower levels of the network to retain that information that we want to extract. Basically, why convolutions is because we have this, so you have 2D image, and you have a kernel, and basically you have all of the neighboring pixels that are then somehow squashed into one value, and then you have kernel that goes over the image, and you squash the 3 by 3 or 7 by 7 values into one value, and then you create like a smaller feature map, and then smaller and smaller. What basically it means is that you just propagate features from original image through the bottom layers to the lower layers of the network, where you just try to compress and extract most relevant features. That's the idea of the convolutional neural network. So this is de facto standard for the past, I don't know, 15, 20, 30 years of how computer vision worked. Okay, so we had a good progress in the field of transformers and in the field of natural language processing algorithms. Sorry. So in the 2017, we had the first attention paper that described how we can attend between different words, right? So I'm now switching to NLP. And then people started to put more and more effort into those attention mechanisms and how transformers work, and I think most of you know that by already. In 2018, we had data, which is they tried to make image classification as a set prediction problem, which was basically something in the field of transformers, but not using convolutional neural networks. And then we started to see the more and more advancement in LLP, which then scientists tried to convert and try to use it on the image processing. What people discovered is that if you can use words, and then when you have when you have attention model in NLP, then you have words, you have sentence, and then you try to calculate attention between every two words. Right, so you have like a quadratic matrix where you try to find this word attends to this word or this to this word, and then you try to find connections and try to find best way how to describe that information in the numbers, in the vectors. Okay, so people started thinking about, can we use that to can we translate that to image classification problem? And there was 2020 they did image GPT. Which they tried to solve that. However, words that we currently use are already compressed information. So, for instance, if I say grass, you already think that grass is green, it's on the field, and you have that. In the image, you can now in the head you can picture that grass, right? And with the image of the grass, you have too many information, too many pixels, too many numbers to describe the grass. So IGPT tried to do is they tried to use each pixel is like 8 bits times 3 channels, so that's 24 bits. What they did try is that, let's make each combination of those bits a vocabulary size and try to encode that and try to calculate attention from that and stuff like that. What they did find is that it was pretty computationally so it was expensive and it was costly. So, but it was really good step forward. And then in 2020, researchers from Google put a VIT paper, which is what we're going to talk about today. Basically, in order to reduce the number of input elements and reduce the number of input pixels, they did something like this. Now I'm going to show the image of an architect. Oh, sorry, just one before. So after the width, we have now active research in all of those, like how to solve different problems that we have with width architecture. We are going to talk about these problems later on, but this is like an active and ongoing development currently in the world. Okay. So quick recap of this architecture. On the right, you can see the transformer encoder, right? So transformer has encoder decoder in this particular use case. We just need encoder because we are not generating anything, so we don't need decoder part of the transformer. And this encoder is basically pretty, you know, there is something gets in, like this embedded patches, we will talk about that. Then you have like pretty classical encoder architecture, multi-head attention layers, and you get that, you do that several times, and it outputs the stuff that you use to get the classification results. Okay, so what the idea was is that since we cannot use all of the pixels because it's computationally too expensive, researchers from Google actually did this. They split image into the small patches, right? So in this example, we have image, and then it's split in 3 by 3 patches. So it's 9 patches. Those patches are first flattened, right? Because transformer encoder works with vector, not with matrix. So you need to flatten it to get the vector. You do some linear projection to transform that vector into some embedding, and then you add something like, it's called position embedding to that, and then you put all of those, so now you get the tokens that you can feed to the transformer encoder. Okay, so this is like, why would we want to do this, basically? Because now we have the ability, since we split the image in different patches, now the transformer will learn relationship between the patches. And you know, in convolutional neural network, we had that kernel that goes and has a locality, right? So all the neighboring pixels are moved to the lower levels. In this architecture, we have like a global attention, which means that one patch can be, so if you have one patch here and one patch there, network can learn that if you have those 2 patches that are now in the space, there is a great distance between them, they can be closely correlated, and network can learn that. We are going to use the word inductive bias. So classical CNNs have something that's called inductive bias, which actually means that we as a people have engineered the network in such a way that we told the network, okay, this is how you're going to squash pixels, this is how you're going to do pooling, and this is the math you're going to do in order to extract features, right? So from handcrafted kernels to handcrafted methods. But now idea is with vision transformers is that you have like a general network that's applied to NLP or image classification problem, that you can apply that network to other types of problems where you can just put the images, put the classes, and say, hey, you learn the best way of how different areas of the image interact with each other. And now the model will try to connect different parts of the region, different types of the image, and try to find what areas would describe best and try the correlation. In the CNNs, so you have like a small locality, and then in this attention mechanism, each pixel can attend to different pixel in a different part of the image, which allows us to extract more global information about the image, not just the things that just go through the layers and we squash them together to get the features. Basically, why we need position embedding is that we want to retain. So the position embedding is just a number. It's not 1, 2, 3, 4. There is a formula to calculate that number, which basically involves sine and cosine, because we want that to be independent of the number of the patches. However, we just want our patches to be numbered, so the transformer can learn which patch correlates to other patch and can extract that kind of information. And that's basically it. We feed it to the transformer encoder. It will learn. We can then connect at the first head. We can connect the like multi-layer perceptron. We can connect any other classification method to extract the most relevant information, basically. Idea was that we basically now have, so when you train network like this, you will see that CNNs have like strong inductive bias, sorry for the typo, and then VITs don't have that bias, which means they will try to learn how to extract features and how to attend to those pixels. What that means is that researchers from Google found out that those models are really data hungry, which means that you need to train them on a million and million of images in order to get that information out of the images. So they train on 300 million images, and Google trained that on a non-publicly available data set, and they created a base model that performs that offers some results better than current ResNet if trained on that amount of images. Which means that if you need that amount of data to train, you won't be able to train it yourself, of course. But with WITS, you can also do the fine-tuning, so you can download their base model, and then you can fine-tune it for your specific classification problem. That works really well. And it can be easily parallelized. So if you have it, then you have this transformer part, which can do matrix multiplications in parallel, right? So you have those key value query, what you have in attention mechanism. You have those matrices, you need to do a lot of multiplications, and you can do them in parallel or in distributed computing. With classical CNNs, you need to wait, so you have one layer, you need to wait for the results of that layer, and once those results are finished, you need to move to another layer. And you move the kernel, and it's harder to parallelize than WITS. So that offers some speed up in doing image classification. Also, so now we have like, in WITS we have global relationships, and WITS try to capture those dependencies between different patches. In CNNs we have spatial hierarchical structure because we move to deeper layers and we try to put more and more information that we go to the lower levels into smaller amount of numbers. How can we see what CNNs and WITS do and work? Is basically we can see feature maps in CNNs, right? So you can see those kernels, and we can see feature maps of different images. We can see, okay, they detect this stuff, and we can maybe visualize kernels through the different layers. There works that to do that. I think TensorBoard has plugins to do that. In vision transformers, we can get something called attention map. Attention map is basically if you go to attention, if you go to the encoder and you pull the weights from different heads, you can draw them. Sorry, you can draw those weights, and you will actually see what each of the heads sees and what do they put attention to, right? So, for instance, we have this, I don't know, we have this broom in the middle, and then you can see that one head will put attention onto the broom handle, and then another head will put attention on the sweeping part, you know, the hairy part. And basically now, when you have those kind of attention maps, it allows algorithm to do the different versions of what you want to classify, right? So this is something that you will now put to some classification part, and then you can actually get the better result. Just a second, you can see the drum part. So basically you have a symbol and a stick. One attention map focuses on the stick and another just purely on the symbol. So what we have here is now we will show the different. This is just purely informational, so you can see that your model will learn the features and will learn those attentions, and you can visualize them and you can verify that this works properly. Okay, let's talk about performance a bit. So let's just take a look at the right-hand side chart. We have MobileNet v2, and basically you can see on the y-axis we have accuracy, and then on the x-axis we have model size. What we can see here is that MobileNet is more accurate, around 73%, if the model size is 3.5 million parameters. And then what we can see is that if you put more parameters and you have greater model size and you put more data in it, this T2T width will outperform and will be more accurate, which means that you can get more out of width if you feed it more data. On the left-hand side chart, you can also see that ResNet has less operations. So we have max as on the x-axis, and you have less operations, but accuracy is around 80%. And then with widths, you can get more accuracy if you increase the model size, but you also get more matrix multiplications, but then you can parallelize them and you can get more, you can get faster response times. Okay, so obviously we cannot train our own widths for business purposes, but we can download the pre-existing pre-trained widths and pre-trained models and just fine-tune on them. Okay, so problems with widths, of course, we have a lot of problems in this domain, is that since we split the image in the beginning, we split the image in patches, you cannot do fine-grained tasks like segmentation, because you don't have that, the mask that you want from object to detect or to segment. So you just have patches, and then within each patch you have some information that's correlated to some other patch. Tricky part is that how can we do segmentation? Basically, there are some advancements in this field where it's trying to be done. But right now, if you want that kind of low-level and fine-grained details extracted from the image, you cannot do that. What widths are good is image classification, and they can also be used to get more descriptive image meaning. So you can use it to, I don't know, create sentences. If you give it image, you can create sentences from that image. Those are the references, and just to show you that this research is currently under research. And I'd just like to do quick summary. So basically, we moved from the NLP domain to the image processing domain. We actually currently the AI technology is in that field where you have advancement in one field and it's basically translating or can be translated to all the other fields. So in this field, we just scientists try to use NLP attention mechanisms to image processing and to do some image understanding better than CNNs, and basically just shook the CNN world. We actually saw that it's computationally effective and can be achieved. This can be achieved through parallel processing. We have different methods for this, right? So we have these patches and extraction of patches and embeddings, while CNNs use kernels. And if you are trying to do this for your business needs, just use the pre-trained widths, download, and then fine-tune them on your image data set. And that's it. Thank you.
Okay, let's see if we have some questions. The first question here. Can we get the microphone? Yes.
Thank you very much for the talk. Very interesting, I have to say. So if I understand correctly, you have to do the segmentation because you're not able to do this encoder part on the full image, right? It's too computationally expensive. I was wondering, can't you do some kind of transformation, like, I don't know, like pooling, just to reduce the image and then not segment the image? Because I think you have some complications then with the segmentation part, right? So you can avoid segmentation, just do pooling.
Yeah, so that's the part. You know that in the architecture, oh, we don't have presentation. Okay, so in the architecture part, you have those layer that converts, linear layer. What scientists try to do is maybe change that with a classical convolutional layer, between then feeding it to transformer encoder, right? So the idea was that can we extract some kind of features that way, and then you can mask some other features, some other values or pixels, and then train on those. And it's called like a hybrid model, and there has been some advancements in that. So in this model that I've demonstrated, segmentation is not possible, but there are some models that can do basically segmentation on that part, but it's not yet better than doing it in a classical way, like if you have CNN way, right? Thank you.
Here?
Sorry, guys.
It's coming.
Thank you, very good presentation. So just one question now, you talked about object detection and segmentation, but so these are like detection mechanisms, but like generation mechanisms, image generation is all the hype now. So basically, do you think that this VAT or transformer-based architectures are the future also of image generation as well?
Do you think they can do image generation?
No, I know they can, but the question is, are they the future actually? Like, do you think like going forward we will have like transformer-based architectures for image generation as the default, right?
Great question. So scientists actually try to do image generation using this, and they can. I'm just trying to remember the paper. There was an elephant with butterfly ears. So if you can Google that, I think that's the paper that talks about generation of images using this method. However, I think the problem currently is that you have to output too many pixels, because with the NLP you have the masked word, and then you learn on the masked word, and then basically here, if you output many pixels, it will get noisy over time, but it gets some results that are okay-ish, right? But to read more paper, I don't remember the paper name, but there was an elephant with butterfly wings as ears. I know that they were working on that stuff.
Thank you.
Here.
Yes, so you have showcased a slide where you showed basically some images and then plotted the attention on those parts of images, for example, the drum and so on. So my take would be that basically what we were seeing were just edges being detected.
Can you just put the microphone?
Yeah, sorry. So my take on that slide, where you had the images and you were plotting the attention, is that more or less we were just seeing edges being detected. So despite this being a vision transformer, and now comparing it to a typical convolutional neural network, did you ever check the same image and then try to plot the same map? Because then you would get maybe some kind of a visual reference, whether it's really paying attention to some object that is in that image or just an edge that is more pronounced in that image. So my question is, if you did such a comparison and if you could kind of visually, as a human, make a distinction whether the attention is really being put on the object in the image or merely on the edge in the image.
Okay, great question. So edges are high frequency features, right? And then if you have a flat colored surface that doesn't have many changes in the pixel values, you have like low energy, low frequency representation. So basically all of those like CNNs and vision transformers will usually learn edges and corners, and from the last 60, 70 years, we have edge detectors and corner detectors and stuff like that, and handcrafted kernels were like Sobel or Harris detector just did that. right? So basically, they learn the color representations through different channels, right? And they learn the color values, but they will always extract features that are high energy and high value, right? Like changes, abrupt changes in the contrast or color or stuff like that.
So maybe then just to follow up, so then it seems as if the typical NLP architecture is trying to be adapted, whereas you treat an image like a sequence of texts, and then as you mentioned, because there is some error in making these tokens, you try to apply some maybe low-level CNN to get some edges and then feed this into the vision transformer, if I understand correctly. Okay, so then maybe, this is just a thought, at some part now it seems that the input is trying to be manipulated in such a way that it fits into this architecture that was developed maybe for text classification. Or what is your take on that? Is it an architecture, vision transformers, that is aimed to replace and work with images, or is it basically, are we now just trying to manipulate images so that they look more text-like and maybe have a lower granulation of information with some adaptive techniques so it better performs than in this vision architecture?
Oh, okay, great question. So the problem is like, are we trying to use, this is some architecture that works for NLP problem, can we use images or audio or whatever other problem and try to fit it there? Yeah. Okay, so beginning of the image GPT article, scientific paper starts with, if you look, this isn't a direct quotation, but it starts something, if you look at the words, and then if you look at the pixels, we can imagine that each pixel is one word. And then can we use that to train the transformer? So basically that was the idea. And I think that you can try to shoehorn every problem now into the transformer network and see the results. And I think this is why this is such an exciting era, because scientists and people are doing the work that they're trying to use different solutions for different problems and try it on their own problems. And now we're getting more and more interesting results of how to do that. Because like Igor said before me, some guy just added, the documentation from the OpenAI and then feed it to some image detection, and then it worked, right? And I mean, he was the first to thought of that, and he even put the API key down there. So I think it's great that if we can show that a transformer architecture can work well on images, because it means that we are getting to some model or some mathematical concept that can describe the world around us better than classical convolutional neural networks. Thank you.